Okay, we're at our second lesson on circles. Last time we did lesson 7.6, I believe it was, and that was your introduction. Had a lot of background information and definitions. Also talked about the difference between arc measure and arc length. Just as a quick review and maybe an addition that I left out last time, if you're naming a chord connects 2 points on the circle. So if that you have that chord AB, it is a segment, so you name it as a segment. So you could say chord AB, or if you said name the chord, you would name it with segment notation. Okay, if you're talking about the arc, the minor arc, which is less than half the circle, you put the little frowny face on top, and that would be arc AB. If you went the other way around, you'd have to name it by 3 letters, maybe ADB, and it would also have the arc notation. Okay, if it just said find AB like that, that means arc length. If it says find the measurement of arc AB with the little M in front, very similar to how we did angles, this actually means to find the measurement of it in degrees, whereas this means to find the length of the arc. Okay, so just a little reiteration from that last lesson. We're now skipping to chapter 11, even though it's a pretty easy progression. We're going to talk about tangents. Okay, you may know this, you may not. It just depends on your background once again. So if you have a circle and you've got a line that intersects it in exactly 1 point, that's called a tangent. Okay, so this line is tangent to the circle. And there's a couple of theorems that go along with it. The first theorem says that if you have a line that's tangent to a circle and you have that radius drawn to the point of tangency, so this is the point of tangency, anytime you draw the radius to the point of tangency, it makes a right angle. So like I mentioned to you last week, look, there's a right triangle. So you got right triangles that are going to pop up on a routine basis for the rest of the semester. This is also a theorem that works backwards. So if you know that those two segments are perpendicular, that would mean that this line is tangent to the circle. Okay, that's theorems 11.1, and then going backwards would be theorem 11.2. Okay, the other thing you need to know about tangents is that if you have an external point outside of your circle and you draw 2 tangents, those 2 segments from the point of tangency to your external point, they have to be congruent. Okay, and once again, that's a theorem. It can be proven. I think the way to prove that would be to put in our last theorem we talked about and said that those would be right angles. You could draw this and you could use the right triangles, prove that they are congruent, and then you could conclude that these 2 segments must be congruent by CP/CTC. So that would be the plan for the proof of that theorem. Okay, that's theorem 11.3 out of your book. That covers most of it. There's one example I want to go through, and then also a couple more ideas with tangents. 2 circles can be tangent to each other. So if 2 circles touch at 1 point, those 2 circles are said to be tangent to each other. Those would be externally tangent. Okay, that would be different than if I would take this circle and then put one on the inside of it, so they touch in 1 point. Those would be also be tangent to each other, maybe internally tangent. And then the other idea is how many tangents you can draw on 2 circles. So if I have 2 circles, you could draw 2 what's called common external tangents, there and there. Okay, and then let me change colors. You could also draw 2 common internal tangents that will go in between the 2 circles. And I'm trying to draw upside down here, so I'm doing the best I can freehanding it. And there you go. So 2 common internal tangents, 2 common external tangents. I want to look at the example. This goes with example 2 on lesson 11.1. And it's a very common problem that you'll see, and I do believe you'll see this on your test as well. But it's talking about a bike chain. And we know that the radius of the small circle is 2.4, and the radius of the large circle is 9.3. And you also have given that this segment at the top is 26.5. The question asks you to find the distance between the center of the circles. Okay, so you're actually looking for the segment that connects the two circles, which would be right here. Okay? What you want to do on this is you want to make a rectangle out of it. You want to go from the center of the small circle over here, such that you just created a rectangle, because you know that's a right angle and a right angle from the theorems we just had. So if this part's 2.4, then this part would be 2.4. Okay, also if this side's 26.5, so is the opposite side of that rectangle, 26.5. And now you use this long skinny right triangle with a 26.5. You're looking for x, which is right there. And then 9.3 minus 2.4, I think is 6.9. So we'd use Pythagorean theorem. 6.9 squared plus 26.5 squared equals x squared. You're actually looking for the hypotenuse. And if you were to solve that, you would get something bigger, which would be 27.4 approximately. So that goes along with example 2 in the lesson. And I think that's covered everything in a lesson 1, 11.1. We'll see you next time for 11.2.